So in this video, I'm going to show you how to calculate a definite integral using U-substitutions. Now there's two ways to do this, and I'm going to walk you through both of them. So the first thing I want to do is I want to actually calculate the integral in terms of U. Okay, so first I need to do is convert this to be in terms of root U. Now it's in terms of x's, so let's get rid of those x's. So let's let u equal sine x. Okay, so everywhere I see a sine x, I'm going to replace that with u. Now I need a dx to get rid of and a cosine x to get rid of. Well, if I take the derivative of u, I get du equals cosine x dx. Lo and behold, exactly what I want to get rid of. Okay, so first option, I turn this integral into u du, okay? And I've got a situation. Right now, my integral limits of integration are in terms of x, okay? Option one is we take this indefinite integral, before we put the numbers here, it's an indefinite integral. As long as I don't have any numbers here, it's just an indefinite integral. And I can go through and I can integrate this with respect to u. The integral of u is u squared over 2. And then what do? I take this, it was originally in terms of x, I'm going to convert it back to be in terms of x. So everywhere I see u, I replace it with sine. So this becomes sine squared over 2. And now I go back to same old, since it's in terms of x. Since I have an x equals pi over 2 here and an x equals pi over 6 here, those are my bounds, limits of integration. Then I'm going to integrate from pi over 2 to pi over 6. F of b minus f of a gives me sine of pi over 2 squared divided by 2 minus sine of pi over 6 squared divided by 2. Now, you think about a unit circle. A unit circle, pi over 2 is right up here. So sine of pi over 2, this is 1 here. Sine is the y value. So that would be 1 squared over 2. And then the sine of pi over 6 is here. This is square root 3 over 2 comma 1/2. So that's 1/2 squared over 2. 1/2 squared is 1/4, and a half of a fourth is an eighth. So all this here is an eighth. Okay? So whenever I simplify here, I get 1/2 minus 1/8, and that gives me 3/8. Option 2, and by the way, this is actually my preferred way to do it, but whatever you like to do, you do it that way, okay? I like to take my integral that's in terms of x, convert it to be in terms of u, and because it's easy to integrate u, okay, and then once I get it in this form, then I convert it to x's, because that's what I have done in even the indefinite integrals where I just find the antiderivative. I always have to convert it to x's, right? So that's just kind of, I'm a creature of habit. I like to do the same thing over and over. So what I do is I take my integral in terms of x, I do a u-sub, I write it in terms of u, I integrate it, and then I substitute back in to be in terms of x. Those are the same steps that we've done all along for U-substitution. The only other step that's added with the definite integral is I do f of b minus f of a, okay, once I've substituted back. The other option, instead of trying to substitute the x's back out, what we do is we convert these x bounds into u bounds. Okay, so now it's u equals something to u equals something. Well, the problem is right now I have these bounds in terms of x's, but u is equal to sine of x. So I'm going to use that fact here to help me out. So I'm going to convert this to be sine of x, okay? So that means that this is sine of pi over 6. Why? Because this is x equal pi over 6, so I plug a pi over 6 in for x to get the lower bound. And then the upper bound is pi over 2, so I'm going to take sine of pi over 2 and plug that in to get the upper bound. And so then what I see is I had the integral from pi over 6, sine of pi over 6, which is 1/2, to pi over 2, which is 1. So now I integrate, and so what is this saying here? This is saying that the integral of u du, which is a line that passes through the origin with slope 1, from 1/2 to 1 has the same area of sine x cosine x from pi over 6 to pi over 2. Kind of interesting, okay? And so whenever I integrate this, I'm going to add 1 to the exponent, divide by it, and I'm going to integrate from 1/2 to 1. So f of b minus f of a is f of 1 minus f of 1/2. And whenever I do this, I still get the same exact answer. So really, it just depends on which one you'd rather do, okay? So something I just thought about doing that might be interesting is graphing this. So let's graph these two things, okay? So I'm gonna graph these two things here. Let me just erase this for a second. Okay, and so the u function, I'm integrating this thing from, so u passes through like this, right? So this is u, okay? And then I'm integrating from 1/2 to 1. So that means that I'm looking for this area right here. Not that hard to put together, okay? And it looks all nice and pretty. Now, if I graph sine x cosine x, actually I'm going to go ahead and use my calculator to help me out with that. Sine x cosine x, let's see what this looks like. So let's clear this. Sine of x multiplied by cosine of x. Okay. All right, so from, what did we say? Pi over 6 to pi over 2. So what is that? 1.57. That seems like pi over 2. Is that right? Let me see. Let's do pi divided by 2. Okay, yeah. So pi over 2. Okay. So if pi over 2 is there, then the pi over 4 is going to be that top part. Okay. So pi over 4, pi over 2, pi over 6. All right. So what's going on with this? The graph comes up to here, and then it comes back down to here. So the graph from here to here, this area here, is the exact same as this area here. These two areas are equal to each other. Kind of interesting that you take some weird looking function like sine x cosine x from a weird pi over 6 to a weird pi over 2. And that's the exact same area as if we had gone from just a straight line and gone from 1/2 to 1. It's kind of an interesting idea that we can convert this area that has a weird boundary here into an area that's basically, I mean, guys, I guess that would be a trapezoid, wouldn't it? So we know how to find the area of a trapezoid without even using calculus. So kind of weird that this area gets pushed into the shape of a trapezoid with a U-substitution. So really the idea here is that the U-substitution takes something that's really complicated and turns it into something that's really not complicated at all.